Okay, I'm making this video in class as we study for the Unit 5 test over IVT, MVT, EVT, and a little bit about optimization. So this first FRQ we are asked to consider, so we're going to consider it. Consider the function which is the cube root of x plus 2. Okay, so if you know anything about your pre-cal, right, you should be able to have an idea of what this looks like. Right, the cube root of x plus 2 is moved 2 units to the left, and it is a cube root function, so it's like a windmill, something like that. That is a very rudimentary sketch, but kind of have that in your brain as we're doing these problems, thinking about what it looks like. Because part A says, what is the absolute minimum value on the closed interval from -3 to 6? So way out here. We're only considering from -3 to 6, looking for an absolute minimum. Okay, and because this is a continuous function, we can apply the extreme value theorem, which says if you have a function that is continuous on a closed interval, there's going to be an absolute max and an absolute min. Okay, so we're going to have to find them. So there are 3 things that we're looking for. Number 1, it could happen at an endpoint. So it could happen at -3, or it could happen at +6. Okay, or it could happen at a 0 of your derivative. Okay, or where your derivative is undefined. So there are 2 things that we need to check. Is where is the function going to have a vertical asymptote, or where is it going to have a maximum or minimum value? So we do that by taking the derivative of our function. Okay, now this is a cube root function. So hopefully you know how to take the derivative of a cube root function. Okay, the shortcut says we have 1/3 times the cube root of the inside thing squared. Okay, and that comes from years and years and years of taking this the long way, which would be probably writing it as a power, x plus 2 to the 1/3 power, and then using the power rule in order to derive that function. Okay, you come up with this thing right here when you do that. Okay, times, of course, the derivative of our parentheses, which is just 1, so that doesn't actually add anything to our derivative. Okay, if there were a number in front of x here, then we would have a number on top as the derivative of the inner function. Okay, so when is that equal to 0? That's the question that we're going to answer. When is our derivative 0? Okay, and hopefully you see that the only time this is going to be 0 is if our radicand in here, right, if this thing is 0. Okay, in fact, if the denominator is 0, then this function is going to be undefined. Okay, so what number plus 2 equals 0? -2 is the answer. So that is where f prime of x is undefined. Right, because that gives you a 0 in the denominator. Sorry, this green is not very visible. Let me change to something that you can see. So the derivative is undefined when x equals -2. Okay, so that's another point we're going to check to see if the y values are larger or smaller than your endpoints. Okay, there are no other zeros on this function, so these are the only 3 ones that we need to check. Okay, so we're going to go into our original function and plug in -3, -2, and 6 and see what we get. So doing this analysis, we see that -1 is going to be the smallest y value on this interval. Okay, so the answer, what is the absolute value, smallest minimum value on the closed interval? You would write something like this. Okay, so this is how we bring the whole entire question together. We were asked for an absolute minimum of a function on an interval, and we gave them the answer. Okay, this would be a 3-point question on your AP test. There would be 1 point for taking the derivative. There would probably be 1 point for figuring out these values, and there would be 1 point for your answer. This would be a 3-point FRQ question. Okay, now letter B. What is the average rate of change on this interval? Okay, so this is where you're going to receive 1 point from the FR or from the AP committee, is by showing this math that you know the average rate of change is by doing the slope equation. Okay, you'll receive 1 point for writing that down. Don't just write down the answer. I know you're smart enough to do it in your head. Okay, but write down, let the AP people know that you know what you're doing. Okay, and that it just wasn't some random lucky guess out of the blue. So we write down f of 6 minus f of negative 3 over 6 minus negative 3. Okay, and we already did these calculations up here, right? F of 6 is 2. F of negative 3 was negative 1. And then this is 6 plus 3 on the bottom. So we have 3 over 9, which reduces to 1/3. So you would get 1 point from writing down the average rate of change formula, and you'll get 1 point by answering the question. Okay, part C, on what interval is f of x decreasing? So we already knew that f prime of x is undefined at x equals negative 2. Right, we found that in part A. That's where our derivative is undefined. So we want to see where is the derivative negative, because where the derivative is negative, your function would be decreasing. So our critical point is negative 2. That's where our function is undefined. So we're going to do a sign analysis on numbers less than negative 2 and on numbers greater than negative 2. So remember, this up here is your derivative. If you plug in a number less than negative 2, like maybe negative 3, okay, we get all of this is negative 1. And then we square it, and we get positive 1. And we take the square cube root of a positive, which is a positive, okay, times a positive 3, all divided by positive 1. So to the left of negative 2, the graph is going to be positive. I said positive literally 4 times in the last sentence. So positive on the left, increasing on the left, and let's see about to the right. What if we plugged in 0? What if this is 0? Then that's positive 2 squared, which is a positive. And then we take the cube root of a positive, which is a positive. You multiply that by positive 3, and then you divide by positive 1, and we get a positive. Okay, so where is the function decreasing? Never. So we would write something like this. Is never decreasing because f prime is never negative. So the only way the function will be decreasing is if we have a negative derivative. So we would get 1 point for the answer, right, that it's never decreasing, and 1 point for your justification, that sign analysis. Okay, and then lastly, does f of x have a point of inflection? Okay, so hopefully you remember points of inflection come from the second derivative. Okay, so we're going to find out where the second derivative is equal to 0 or undefined, and then we're going to see if there's a sign change there. Because if your second derivative changes from positive to negative, then your graph goes from concave up, where it's positive, to concave down. Okay, and that's a point of inflection. So let's see, our first derivative was this crazy function right here. So let's take the derivative of this. Let's practice our power rule. We're going to bring the negative 2/3 and multiply it by 1/3, which is negative 2/9. Okay, x plus 2 doesn't change. We're going to subtract 1 from our power. So we're going to subtract another 3/3. So negative 5/3. And then times the derivative of your parentheses, which is just 1. So nothing is happening there. Now remember, we want to know when this is equal to 0 or when it is undefined. So it looks like it's going to be equal to 0 once again when your parenthesis thing is going to be 0. So what number makes this equal to 0? Negative 2 does. Okay, so that's going to be the point that we're going to test for our sign analysis at negative 2. So if we plug in a number less than negative 2 into your second derivative, okay, like say, oh, I don't know, negative 3, then this is a negative 1. right, raised to a negative power. So negative raised to a negative is going to be a negative. But then we're going to multiply it by a negative. And what's a negative times a negative? A positive. So to the left, we're going to have positive. The graph is concave up. And what about if we plug it in 0? Then that's a positive 2 raised to a negative power. Right? So 1 over something, what's that? Actually 2 over, right? Negative 2, 9, the third root of x plus 2 to the 5th. So we have 2 to the 5th, which is positive. The cube root is positive, times 9, which is positive, but divided by negative 2, which is a negative. Okay, so does this have a point of inflection? Yes, it does. Yes, f double prime changes from positive to negative at x equals negative 2. So when we have a sign change of the second derivative, you have yourself a point of inflection. Okay, so looking back up at our graph, right, to the left of negative 2, it's concave up. And to the right of negative 2, it's concave down. Okay, so all these answers make perfectly good sense based upon our graph. Okay, awesome. Let's try another one. Let me bring it up. Hang on. So here we are considering this function, this cube root of x squared plus 2, between positive 1 and 8. And they're saying that there's some value c that equals 4. So we want to verify the intermediate value theorem. So number 1, we have to say it's continuous. If the function is not continuous, then we can't use the intermediate value theorem. And then number 2, we have to find the y value for your endpoints. Okay, we have to do these two things. So let's see, what is f of 1? That's the cube root of 1 squared plus 2, which is 3, right? Because the cube root 1 squared is 1. The cube root of 1 is 1. 1 plus 2 is 3. Okay, so then we're going to do the same thing for 8, f of 8, the cube root of 8 squared plus 2. So let's see, 8 squared, that's 64. The cube root of 64 is 4. The cube root of 64 is 4. 4 times 4 times 4 is 64. 4 plus 2 is 6. Okay, so is there a c value that's going to be equal to 4? Yes, there is. So we have to state that explicitly. Okay, so this is the important part for calculus, saying all of this. Okay, verify that it is applicable. We have it being continuous on the closed interval, and our y value of 4 is between the two endpoints that we have calculated. Okay, so the IVT is going to apply. So now find the c guaranteed by the IVT. Right? So now we have to do a little bit of math and figure this stuff out. Okay, so we want to know, when is this function equal to 4? So 4 equals the cube root of x squared plus 2. Okay, at what x value gives us a y value of 4? Right, so we'll minus 2 from both sides. 2 equals the cube root of x squared. Okay, our next step is to cube both sides. That's raising it to the third power. So 8 equals x squared. And we solve this lastly by taking the square root. Okay, now of course when we square root things we get positives and negatives, so don't forget x can be two values here, but which one is in our interval? positive root 8. Okay, positive root 8 is on the interval from 1 to 8. So we have one answer for our problem. Okay, this would probably be 2 points. You'd get a point for figuring out this one, and 1 point for the answer for your 2 points. Okay, verify that the mean value theorem can be applied on this function on the indicated interval. So the mean value theorem says that there is a point where the derivative equals the average rate of change. Right? The instantaneous is equal to the average on this interval. So we have to make sure that it is differentiable on that interval, right? So we have to make sure that this occurs. So let's take the derivative and see if there are any undefined values over here. Okay, so where we have cube root of x squared plus 2. Okay, so I'm going to write this as a power. This is the 2/3 power plus 2. And now I'm going to take the derivative. So we have the 2/3 that come to the front to the negative 1/3 times 1, because that's the derivative of x, and then the 2 is constant, so there's no derivative for that. Okay. So what value will make this thing undefined? That's what we're asking here. So we have x in the denominator. So x cannot be equal to 0, because if x is 0, then that function is going to be undefined. Okay? But is that a problem for our interval? The answer is no. Our interval goes from 1 to 8. Okay? So that's fantastic. The function is derivative on our closed interval from 1 to 8. So we can, well, I guess that's really all we have to do. So f prime is differentiable. Sorry, not f prime, but f. Let's erase that f prime. F is differentiable on the closed interval from 1 to 8. Actually, differentiable on the open interval, right? That's what I meant to say. Differentiable on the open interval from 1 to 8. And continuous on the closed interval from 1 to 8. Okay, so it's undefined at 0, but it's continuous everywhere else. Okay, so find all values of c that will satisfy that MVT. So now we're looking for f prime at c, okay, which is f of 8 minus f of 1 over 8 minus 1. So now we're going to have to do a little bit of calculating in order to figure these things out. So let's use our values from the first thing. Sorry, f prime of c, not x, equals the f of 8 is 6 minus f of 1, which was 3, over 8 minus 1, which is 3 over 7. So we're looking for a place where the derivative is 3 over 7. Okay, and our derivative over here, remember, was this 2 over 3 times the cube root of x. So we want to know when this equals 3 over 7. Okay, so we have a fraction equals a fraction. Let's cross multiply. 7 times 2 is 14 equals 9 times the cube root of x. So we divide both sides by 9. and then cube that. Okay, which because this is a non-calculator, the cubed or 14/9 cubed is perfectly fine. Okay, 14/9 to the third power. That is going to be your answer for where our function has a 3/7 slope. Okay, 3/7 slope. So you take the derivative of our function and you set it equal to the average rate of change on that interval. Okay, and then you do all of your wonderful math in order to solve that for x, or in this case for c, I guess. If you change all the x's to c's. But variables, schmariables, I think it would be okay. And then the last question, name an interval where the MVT could not be applied. Okay? So is this function continuous everywhere? Yes, everywhere it is continuous. But where is it not differentiable? Okay, not differentiable at x equals 0. Right? So any interval involving or including 0, the mean value theorem would not apply. Okay, so as an example, maybe from -2 to 2. Right? That would be an interval that includes 0. The function is not differentiable at 0, so the MVT would not apply on the interval from -2 to 2. Okay, so you can pick any interval that includes 0, and that would also dissatisfy the mean value theorem. Okay, so hopefully this is a little bit better for what AP Calculus is requiring you to do in order to verify your knowledge of the intermediate value and the mean value theorems.